So I will start with a very basic introduction, but of course, in this community, we all are well aware of the fact that the interstellar medium is under high scrutiny using many instruments. So you have some examples here. It's heavily biased, both in frequency region and instruments I'm showing, but we have these excellent instruments. Some of them are not operating at the moment for Herschel or Sophia, for instance, but we have legacy data, as we've seen yesterday. And they're providing a lot of information on the physics and chemistry of interstellar medium. So of those instruments, of course, we are going to be talking a lot about the James Webb telescopes in the next few days. It's providing us with a lot of beautiful images as the one used in the background. But we also exploit a lot of data at very low frequencies of the electromagnetic spectrum, using like instruments from the microwave to the millimeter wave, sub-millimeter wave domain. For instance, single dish telescopes or radio interferometers. So those instruments, of course, they gave us these beautiful pictures, but we also really like the fact that they provide us spectra, really good quality spectra. We see a lot of lines on those spectra, and when we analyze them, we can identify the molecules that are present in specific environments and their concentrations. This is really good, but it really starts to make sense when you combine this with models, astrochemical models, that really dig into how molecules are formed and how they are destroyed under the condition of interstellar medium. And both these fields, observation and models, very heavily rely on laboratory data, experimental and theoretical, to really make sense of all of this. So you need to provide a lot of laboratory data. It can be rest frequencies so that you can look at specific frequencies in space to determine the presence of a specific molecule. But it can also be data for the models like reaction rate coefficients and so on. So this triangle on the left here, I hope it reminds you of the fire triangle that we learned in school. So it's our own fire triangle. If you put all of these fields together, so you don't have a big fire, but you get a chance to really understand the physics and chemistry of interstellar medium. If you take one out, then everything is collapsing. So perhaps a good example of this like fire triangle synergy is the case of CH3+ that we have seen yesterday already in the talk by Ilan. So this CH3+ ion was supposed to be ubiquitous in space and extremely important for the chemistry of carbon molecules. But it was not found in space for a really long time until James Webb telescopes, and in particular the work done by the PDR4All consortium that are investigating photodissociation region, and in particular the Orion bar, and in one specific region of that bar, a protoplanetary disk that is a small point in a square on the left picture. They observed really fast in their first survey a feature that could not be assigned using catalogs of known molecules that are based using laboratory data. So it was a two-step process to really go through this data and assign it with confidence, but it was eventually assigned to the CH3+ cation, and it was only possible because the field of observation, models, and laboratory spectroscopy work together to really make sense of this observation. So CH3+, it's one known now interstellar molecule, but there are many others. As of last week, about 330 different molecules have been identified in the interstellar medium. So it's a lot, and it's particularly interesting because about a third of those were found in the last 4 to 5 years. And you can see that on the left-hand picture, which is a plot of the total number of known interstellar species as a function of time. You have several changes of slope. The really important one is the recent one, where the curve, the plots start to go really up really fast. There are several reasons for this. The main one is really deep investigation of some specific source by, for instance, TMC1. One of the person in charge of those surveys is actually in the room today. So Pepe Sarneccharo found a lot of those recent molecules. And we hope there are many more molecules to be found, in part because we know there are many more features on astronomical data that are also absent from spectral catalogs like CH3+ was initially. And so we really need to find what are those molecules. And another bias, but if you split that curve on the left in terms of spectral region, you can see that most of interstellar detection, they occur at really low frequency, from the microwave to the terahertz region, because this is where you can observe the rotational structure of molecule. That's the most molecular specific feature that exists on molecule. So it's a primary range for molecular detection. So actually, at the stage of current facilities, astronomical facilities, any molecule that has a permanent dipole moment will likely be found at very low frequency, and only molecules that are centrosymmetric will be found in the infrared or UV range. So why don't we find more molecules as of now? The problem is that our fire triangle is not perfect. Observations, they're excellent. They may likely be better in the future, but for the moment, they're really, really good. Models are really good too. It's hard to know how good is a model because it's so heavily constrained by the data you put in that you can have some fluctuation. But that's the real problem, is the data we put in. We need more laboratory data. There is a huge lack of laboratory data on many, many things. That's why we have this session of laboratory astrophysics, I guess, here today. So this is really the limiting factor in molecular detection. So in the labs, we need to provide laboratory data on many molecules that are thought to be present in the interstellar medium so that we can search for them afterwards. And so in our group, we try to do this. So again, there are many, many things that can be done in terms of laboratory data. So we restrain ourselves to measuring rest frequencies for molecules, because that's the feature you need if you want to identify them in space. We also aim at rotationally resolve, again, so pure rotation most of the time, but sometimes raw vibration. And we also investigate mainly reactive species, so molecules that are not stable on Earth under normal temperature and pressure conditions, because those species remain widely understudied compared to stable commercial counterparts or molecules you can synthesize and store for quite some time in your lab. So those species could be radicals, ions, or metastable species. And so today I'm going to show you one example of this that we've done in the last year in our group on the H2NCO radical. So this radical, it's plotted here on the figure. If you look at it, it's really, really close to formamide. And formamide is a really abundant astronomical species. It's a well-known molecule. And if you remove one H from formamide, you make H2NCO. And that radical is already present in many, many astrochemical models. It's postulated to be really a key intermediate in many chemical reactions and central to some ice grain chemistry schemes. Investigation, but absolutely nothing at high resolution. So the feature required to look for it on radio astronomy surveys were absent. So to do this study, we made our own fire triangle with people from all of these fields. A lot of them are present here today. So from the observation side, we work with Jes Jorgensen and Audrey Kuttens. Jes is actually the person who was the drive in the project. He was the one telling us to really try to produce that radical in our lab. Then for the lab, it's Olivier Pirali and myself and ISMO, and the model, Jean-Christophe, from here, actually. So the first thing we've done is, of course, try to get laboratory data on the radical. So as I told you, we need both experimental and theoretical, and most of the experimental work needs to start with some theory. So we need to get an idea of where to look for the radical in the lab. So to do that, we've done some standard DFT calculation, which is providing us with accurate equilibrium structure and some really reliable spectroscopic constants. So we can predict the spectrum with confidence. Usually the constants are good within a fraction of a percent at different temperature. So in our lab, we've done that study at room temperature. So you simulate the spectrum, you look at where are the strong lines, and then you try to find them in your lab. The next step is to produce the radical. It's always a challenge. Most of the reactive species in labs are produced using discharge experiments, radio frequency or electrical discharges. They're really efficient, but they make a soup of molecules. You make really a ton of molecules. And it can be really complicated to find specific features of really, really weakly abundant species. In the past few years in our group, we've been implementing the technique with Jean-Christophe Loison, actually, using hydrogen abstraction using fluorine atoms. So that was a technique that was already in place in many labs, and in particular on the Désir beamline at Soleil. That's how they produce radicals at Soleil. And the idea is that you start from an organic precursor and you have a flow cell and you make it collide with fluorine atoms. And those fluorine atoms are going to somehow catch an hydrogen, produce HF and the radical of interest. So because for most molecules, you have several hydrogens, you have many sites of abstraction possible. So you can make a couple molecules. You can also abstract several hydrogen or add fluorine addition. So you make some molecules, a few of them, but really, really a lot less than with standard discharge experiments in plasmas. So this is kind of a clean production methods, and we found it really efficient to produce radicals in reasonable concentration so that we can detect them with a good signal-to-noise ratio. So we have a few examples at the bottom page here. A few of those radicals were observed for the first time in the gas phase, and we have more that have been done since that picture, and we will show them probably in the next few months or years. So the next step was to, of course, record the spectrum. We have several spectrometers in our group. The first attempt to observe the spectrum was done using a Chirp pulse spectrometer. So it doesn't really matter what kind of spectrometer it is. The idea is that it's a broadband millimeter wave spectrometer. So we get a broad snapshot of the molecular composition of our sample over like quite a wide spectral region. So it's really easy to see at one glance what are the molecules present in our environment. So the Chirp pulse radiation is probing a short cell as shown on the picture, and in that cell, it's a reaction cell. So we have the precursor and the fluorine atom that collide and produce the radical directly in situ, and we probe them at the moment. So the one issue with this, so it's not really pure absorption spectroscopy, but it's related, and it's pure rotation spectroscopy. So the spectra you collect, the intensities of the lines you're going to get are proportional to the molecular abundance and the dipole moment of your molecules present in the sample environment. And the issue is that the precursor is formamide, so it's a strong dipole molecule, and it's of course present in large excess. It's the precursor, so it's maybe 1,000 times stronger than the radical lines we want to find. So basically, when you record a spectrum like this, you have a forest of lines, huge lines, really good lines with good signal-to-noise ratio, and you are looking for a really, really weak signal of something created by your experiment. So it's not easy, and to really help us, we actually process in 2 steps. We first record the spectrum in those conditions, and then we record it again after placing a permanent magnet under the cell. And because of Zeeman effect, this is going to affect all the lines of the open shell species, so the radicals. And basically for us, they're going to disappear in the noise. So the spectrum we record with a magnet will only contain lines of closed shell species. So if you subtract your 2 spectrum, you get a final spectrum of radical-only lines. And this is what we've done for H2NCO. So we've recorded the spectra twice 2 hours, so 2 hours with magnet, 2 hours without it, subtract the 2 features, and we get the dark plot presented here. So signal-to-noise ratio is not really good, but it's a very fast acquisition. And if you compare that to our simulation from the quantum chemical calculation of what we expect H2NCO to be, you can see that it's really closely matched. We have these 2 clusters of lines, and it's also, if you zoom in, partially resolved hyperfine structure. So this is good enough for us to assign the first lines, refine our model, and then look for more lines of a radical at higher frequency. And for that, we've been using another spectrometer, which is a very conventional one from like pure rotation spectroscopy in the millimeter and sub-millimeter wave domain. It's based on frequency multiplication, of a radio frequency synthesizer source. And the radiation, so it's single frequency at a time, and then we can tune it to basically any frequency we want really fast. So you can really scan your spectrum really fast as well. It's a bit slower than the Chirp pulse, but it's still really fast. And the idea in that experiment, so this is closer now to standard absorption. So the longer the absorption path length and the higher the concentration, the best the signal of radical lines. So we have a long cell and we have a double pass in the cell to increase our sensitivity to the molecular lines we are going to see. So you can see the radiation is getting in and out of the cell. And then it's going on to the detector. So detectors for those kind of experiments, they are sensitive to variation of signal. And conventionally, what is modulated is the source frequency, the source of like the frequency of the radiation source. But if you do that, you're back to the case where you still have your precursor and your radical present in the same medium with huge lines of precursor and tiny signal of radical. So it's not really convenient. And so in that case, again, we exploited the Zeeman effect, but this time we could do, I'm going to show you that later. Sorry. Okay, so we could do modulation of the magnetic magnetic field. So the cell is surrounded by a solenoid, and we have an alternating current going through that solenoid. So that means there is an alternating magnetic field around the cell. That means that the lines of closed shell molecules, they're going to be constant in time, while those of radicals, they're going to be fluctuating their intensities with the frequency of a magnetic field. So if you demodulate your signal at this frequency, you can retrieve a spectrum of radical-only species. You completely filter out your precursor, that is, again, really strong, really abundant, and you get radical-only lines. So these experiments was developed by two PhD students, Olivia, who is now done with her PhD, and Rosemond, who is in third year. And this is an example of what you get. So you can do either a small survey around specific portion of the spectrum or larger ones. And in like a few minutes or a few tens of minutes, you can get broad views of the spectrum. And it's radical-only lines. So again, here, the black trace is the experimental spectrum. The red one is the simulation of the H2NCO spectrum. And basically everything you see on the black trace is an expected line of H2NCO. You have a zoom in here on the bottom part, but it's really good. It's also really good signal-to-noise ratio. The structure can be a bit weird, but this is hyperfan structure, so it's a spectroscopic feature. It doesn't quite matter, but it was really easy to assign the spectrum of H2NCO. So with that, we've assigned many lines of H2NCO at room temperature using our two spectrometers. So the Chirp pulse one, the region is here in orange, and the frequency multiplication chain here in blue. The idea was to scan the strongest lines at room temperature, assign them refined spectroscopic parameters so that we can really predict the spectrum of this radical extremely accurately, from 300K down to very low temperature, and from the highest frequency we've been scanning, about 700 gigahertz, down to really low frequencies. So with that, you can really look for that radical in many different environments in space, cold or warmer, and with many instruments, like radio instruments or sub-millimeter wave instruments. So then once you have that data, we switch to the second step of the project, the observation. And we decided to look for H2NCO in the ALMA-PILS survey by Audrey Coutenz, which is a survey in which formamide has been found. It's extremely strong lines, so there was a chance to detect the radicals there. And because the source is quite warm, it's a solar type protostar IROS 162932422. We look for transitions around 350 gigahertz. And this is a view of the observation. So in black, the observation. And in blue and red, two simulations of H2NCO spectrum at different temperatures. And you can see that there is absolutely nothing. So H2NCO is definitely not present in that source. It's not a full nothing, because that means we know it's not detectable, so we can produce an upper bound to the concentration of the radical. And we now know that this radical, if it's present in the gas phase in that source, it's at least 90 times less abundant than formamide. So then you can incorporate this information into astrochemical models. So that was the part of Jean-Christophe. You can see here just a quick view of a part of the results, but You can have here in red the upper limit for the concentration we found for H2NCO, and the dark curve below it is what the model predicts the gas phase concentration should be. So our upper limit is still way higher. Yes, perfect. Way higher than the actual concentration of the now expected concentration of the radical in the source. So as a conclusion for this project, H2NCO definitely not an abundant species in the gas phase in that source. We look at other sources, many different of them. No one has found this radical yet. That doesn't mean it's not important for astrochemistry, but likely its role is probably constrained on ice grain surfaces. If the radical is present in space, it's probably stuck on ice grains, not present in the gas phase, so we can't really detect it. But there will be more data, like maybe with like lower noise level and so on. So maybe the radical will be found in the future. We know that we have like accurate frequency line lists to look for it now. So catalogs are up to date, and maybe someone will find it in the future. So that was not a full failure, but not a success. But this is 99% of our work, let's say. So it's very, very common not to find what you're looking for in space. But luckily for us, there are many more molecules to be investigating in the lab. And in our group, we now have many tools to do this. So we have the two spectrometers I've shown you before. We actually have two of the frequency multiplication chains, so we can scan up to 1500 gigahertz. And those spectrometers, we spend a lot of time in the past few years to make them compatible with many different experimental setups to produce reactive species. So we have many cells. We even have cells for room temperature, like stable molecules, because we also study some stable molecules once in a while. But we have many different electrical discharge cells, radio frequency cells. And we've been developing recently a DC discharge cell with a supersonic jet expansion to do like cold spectroscopy. And I'm going to show you just a quick example from actually last week. This is a very schematic representation of the setup. So you have a supersonic expansion here, and we use the Chapel spectrometer to probe the content of a jet. And you can strike a discharge just at the output of your nozzle. And the precursor or the several precursors you put in are going to be basically atomized, and they will recombine to make whatever product you hope to make. And very recently, we have detected the CH3O CH2 radical, which is dimethyl ether -1H. So this is the work of Rosemond, again, the PhD student. So she has many lines of that radical. She first started with the F reaction experiment at sub-millimeter wave frequency. And now we have detected lines at cold temperature. This is probably about 10K. And you can see we have like a reasonably good enough model for this molecule. So this is going to be presented soon, but we can really detect radical species efficiently. So with that, of course, I'd like to acknowledge the group I'm working in at ISMO. So we are many, but for the rotational spectroscopy part, I'm working closely with Olivier Pierali and the two PhD students, Rosemond and Luan. The picture on the right-hand side is from last spring, so we were a bit more than we are now, but we now are only 4. And of course, the collaborators who worked with me on this project, especially Jean-Christophe and Audrey, who are here today. And I'm just going to conclude by saying, I hope you're convinced we need more lab data on many molecules. And the best way for us to do this is to work closely together, people from the lab, people from the observation, and people from the modelization side. And thank you for your attention.